Okay, hello guys. So I've gotten some requests that people were needing some extra help. So I'm going to do a quick little video to kind of help you guys rank and compare intermolecular forces. So, in general, our first step is to identify the type of interaction we are seeing. So when we identify the type of interaction we're seeing, what kind of examples do we have? We'll go from strongest to weakest. So we have ion interaction. We have ion dipole. We have dipole. And then remember, a specific type of dipole that's extra strong is hydrogen bonding. And then we have our dipole, induced dipole. And then we have induced dipole, induced dipole. So ion is with our ionic solids. Whoa, I can't, there we go, solids. Generally a metal with a non-metal, and oftentimes it'll be like an alkali metal, so that's our group 1, or our alkali earth metals are group 2. This is our periodic table, imagine, and then something over here. So some classic examples are like table salt, NaCl. Here, I'm gonna pause. Okay, I'm back. I grabbed a periodic table for you guys to see. So here we have our classic example, NaCl, or you could have CaO. And if anything that has to do with one of these elements, it's probably gonna be a ionic solid, but you can also have things like iron or one of your like more transition metals, and that can also be used for something ionic, where you're seeing that transfer of electrons. And then we have ion dipole, which is when you have something ionic with something polar. So a classic example of that would be NaCl in water, or with H2O, like salt water, because you have your ionic solid with something polar. Then you have dipole-dipole interaction, which is polar with polar. And you can remember polar is dipole because if you flip a D or a P around, it becomes that letter's like D just rotated as a P, or P rotated as a D. And then a specific type of dipole-dipole interaction is your hydrogen bonding, which is stronger than normal dipole-dipole interactions. And you have 2 requirements for that. It must be polar, and it must be hydrogen bonded to a F, O, or an N, are freaks of nature. So an example would be water again, because if I drew it out, it would look like this. So here we have a polar molecule. We know that because the lone pair on the central atom, so it's polar, and then it's hydrogen bonded to an oxygen. Hydrogen bonded to an oxygen, that's one of our freaks of nature. So this is hydrogen bonding, smiley face. Then we have dipole, induced dipole, and that is when you have something polar with something nonpolar. And then induced dipole is when you have nonpolar with nonpolar. And do you guys remember what the other name for this is? London dispersion. And remember, everything experiences London because everyone wants to go experience London. So yeah, everything experiences London dispersion forces. And yeah, So if you just had something in general where you're comparing an ionic solid to something polar to something nonpolar, ionic's going to be the strongest, then the polar, then the nonpolar, because the strength goes like this. So we have, here I can also just write that. We have increasing strength. Increasing strength. So, but you may ask, okay, Jordan, how do I compare if I have 3 things that are ionic then? Good question. So, what are our 2 things that we look at when we have ion? Comparing ionic, charge, and then size. Charge is larger, charge stronger, and then size is smaller, size stronger. Polar, you don't necessarily, you don't necessarily compare polar to other polar ones unless you have hydrogen bonding. So if you have 2 things that are polar that you're trying to compare between and differentiate the strength, chances are you have something that has hydrogen bonding. So always check for hydrogen bonding if you have something polar. And then for London dispersion, or your induced dipole, your stuff with nonpolar molecules, you compare by the more massive is stronger. So let's apply some of these ideas, right? Let's see what we got. So we'll do number 1 first. And I'll even pull this, if it lets me. Oh, here we go. Sorry guys. I'm gonna pull our periodic table over so we can reference it. All right. Also, you guys can pause. Here, let's just try. You guys pause the video, try to do this on your own. Think about it. And now I will do it with you guys. So let's do blue. Why not? Okay. I have Mg. So what's our first step? Our first step is to identify what we have. So in my first thing, I see we have MgO. So Mg, magnesium, is an alkaline earth metal. So this is going to be ionic. Okay, what about Kf? So Kf, we have potassium. Potassium is an alkali metal. So this is also going to be ionic. And then we have CaO, and we have Ca, calcium, is an alkaline earth metal, so another ionic species. So we have ion-ion interactions. So what did I tell you guys? How do we compare this then? Charges first, that's more important. Charge, and then size. So let's go through our charges. Mg has a charge of 2+, because it's going to lose 2 electrons, because it's here. Then O is -2, because it's going to gain 2 electrons to get to noble gas configuration. Sorry guys, I'm a little sick right now. And then K +1, F is -1, Ca is 2+, O is 2-. So I got my charges, and we know that the stronger the charge, the stronger the intermolecular forces. So, and here we're comparing boiling point. Sorry guys, or here I'll circle it. Boiling point. So it's normal order. So we want our stronger ones up here. So we have 2 of these that have an absolute charge of 4, because you add them up. So, you know, this one's the weakest because it has the lowest absolute charge. So we already know that Kf is going to go there. Okay, so we did our charge comparison. Now we have to do our size comparison since these 2 have the same charges. And then remember, smaller is stronger. So, and our periodic trend is down into the left, gets larger. And O is consistent, so we just have to look at Mg versus calcium. And calcium is larger because it's down and to the left. So magnesium is stronger because smaller, stronger, larger, weaker. So this is MgO, CaO. So just to recap, this is the strongest because larger charge, smaller size. This one's mid because larger charge and bigger. Sorry guys, I cannot write right now. And then this is our weakest because it is our smallest charge. So that's one done. This is one where we compared all of them that were ionic. So let's move on to our next one. So rank the following in order of increasing vapor pressure. Vapor pressure, what happens with vapor pressure? It's opposite normal order. So if I have NH4, Br, F3, and NH3, let's go through. Our first step is to identify what we have. So for first step is to identify what we have. Here we have our NH4. Oh, and you guys can also pause to try this one on your own. You have the worksheet, so you can try to do it yourself. But now let's go over it. I'll just imagine that you guys paused it, and you paused it, and you did it yourself, and you got it right, and now you just want to go over it. Sorry, this video is gonna be all over the place, but hopefully it helps. So we have NH4. NH4, we have N, and our hydrogen is technically here, but hydrogen doesn't count as our metal, so that doesn't count as this chunk, because hydrogen's weird. But we have NH3, so that is gonna be a molecular species. So we know this is molecular. And if it's molecular, I want you to draw the Lewis diagram and see if it's polar or non-polar. So if I were to draw NH4 plus, it'd look like this, because this would give our nitrogen a formal charge of +1. That's where that positive comes from. So this is NH4. And then that is non-polar because it's uniform. Then we have BrF3. So where's Br? Here. Oh, Br is over here. F is over here, so we have another molecular species. Draw this over here, molecular. Then if it's molecular, I want to draw it out to see if it's polar or non-polar. So we have Br, F, 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 and then because Br is in this row, it wants to has 7 valence electrons. So we want it to look like this to get its formal charge to be 0. Here's where it would have a formal charge of 0 because it'd have 1, 2, 3, 4, 5, 6, 7. So this is a polar molecule because we have a lone pair on the central atom. And then we have NH3, so kind of same as before. This is also going to be molecular. And then to figure out if it's polar or non-polar, we draw it out. And NH3 looks like this, with a lone pair on nitrogen to get its formal charge to 0. And then here we also have a polar molecule because we have that, again, we have that lone pair on the central atom. So this is already an issue of a non-polar but 2 polar molecules, but I said you wouldn't have to compare polar molecules. But you do have to look out for hydrogen bonding. So I'm working my CA desk right now, so the number of times I've had to pause and stop what I was doing is many times. So remember, when you're looking at polar molecules, you have to check for our hydrogen bonding. So one of these is probably hydrogen bonding if we're comparing two polar molecules. So what are our requirements? It must be polar, and it must, which both of these are. Then we have to see if hydrogen is bonded to a freak of nature. So here's the only one where we have hydrogen bonded to a freak of nature. We have hydrogen bonded to an N, and this is then hydrogen bonding. So if you remember our list, our order goes for normal strength would be nonpolar would be the weakest, then polar, then hydrogen bonding. But because this is vapor pressure, it's opposite. So it'd be NH3, then BrF3, and then NH4 plus. But yeah, so this one, remember hydrogen bonding because it's polar and has a freak of nature binded to a hydrogen. Because this also has a freak of nature, but it's not binded to a hydrogen, so it does not count. And then this has a freak of nature bonded to a hydrogen, but it's not polar, so this is not hydrogen bonding, not hydrogen bonding. Hydrogen bonding. Hydrogen bonding is the strongest, so that goes last because it's vapor pressure. So hydrogen bonding, polar, nonpolar. All right, let's move on to our next one. What color should we do now? I feel like we should do like orange. Excuse me. Okay, now we're doing order of increasing melting point. So let's see what we got. So we have CCl4. Look at our periodic table. CCl4. We have CCl4. So this is a molecular species. Oh, I want to do orange. Sorry, this is so not. The color I'm doing is not important. Oh yeah, and practice doing this yourself before you watch me do it. So practice. Pause. Play when you're ready. Okay, so it's molecular, and then what do I want you to do if it's molecular? Draw the Lewis diagram to figure out if it's polar or non-polar. So CCl4 is drawn like this. You can add all your lone pairs if you want to, or you can just assume. And this is a non-polar species. Then we have CO2. So if we look over, we can see our CO2. CO2, this is a molecular species. And if we have a molecular species, what do I want you to do? Draw the Lewis diagram. So carbon in the middle, oxygen likes its double bonds. Here we have a formal charge of 0. See if this is polar or non-polar. This is non-polar, because around the central atom it's uniform and there are no lone pairs on that central atom. And then we just have neon and xenon. If you look, neon and xenon are both noble gases, so they're just chilling. They're also considered nonpolar. So nonpolar, nonpolar. So if you remember, how do we compare things that are all nonpolar? Whatever is the most massive is stronger. So we'd have to add up the molecular masses for these. I currently do not have that on me, so I'm gonna have to look up a periodic table that would. Please hold. Okay, carbon. Okay, let's do some math. I'll do the math in like a different, in a yellow, I don't know. Okay, carbon is 12 plus chlorine is like 35.5 times 4. Carbon, we said it, then for CO2, carbon is 12 plus oxygen, which is about 16 times 2 of them. Neon is about 20. And then xenon is 131-ish. So if we did that math out, our CCl4 would be times 4 plus 12, 154. CO2 would be 16 times 2 plus 12, 44, 20, and then 20, and then 131. So this is our most massive. Sorry, I can't spell. This would be our least. Melting point is just normal order. So our final order would be CCl4, xenon, CO2, and then neon gas. Because it went in order of most massive to least massive. Most massive being stronger. And melting points are normal order. All right, we've already done 3. So let's do our next one. Let's do like green. And so here we are going to be comparing, let's see, we're going to be comparing vapor pressure. So if I'm comparing vapor pressure, remember that's opposite. So remember, circle it a million times. Again, this is where you're going to pause and practice yourself and then watch me do it. Maybe, at least that's what I'm saying in my head. Okay, so here we have SF4. And here I'll bring our periodic table back over here so that way we can reference it. Okay, so we have SF4. SF4, here we have a molecular species. And if it's molecular, what do I want you to do to figure out if it's polar or nonpolar? Draw the Lewis diagram. SF4 plus all the lone pairs on the fluorines. Sulfur is not happy like this though because it wants to have the 6. So we put a lone pair on sulfur, making it polar. That lone pair on sulfur makes it polar. Then we have silicon F4. Let's see where that is on our periodic table. We have silicon F4. It's another, hi guys. It's another molecular species. So, molecular SiF4. You put your lone pairs. There's a hold on guys, hold on, please pause. Sorry, not the most peaceful place for me to film right now, but it's the only chance I really have had. I've been kind of busy. Sorry guys. How many times am I going to say that? Someone start a counter. Okay. Silicon, however, is okay just seeing the 4. No lone pairs on silicon. And it's uniform. So this is going to be a non-polar molecule. Okay, and then we have K2O. So if we look at our periodic table, where's potassium? Okay, potassium. Over here, K2O. This is going to be an ionic species. So, okay, had a pause, we're back. Okay, so here we have ionic. So our typical order of strength would go non-polar the weakest, then polar, then ionic. But remember this is vapor pressure, so it's opposite, so it's going to go ionic, polar, non-polar. So our final order is going to be K2O, SF4, SiF4. Look at that, we're doing it. Okay, there you have one more problem that we're gonna do. What? I feel like I've done all the colors. I guess we'll do purple again. I like purple. Sorry. Okay, first step. Well, first we're gonna see, okay, we're comparing boiling points. Good to note. Now we're going to go through and identify what type of forces or what type of interactions we're having. So, KCl2, where is it? We have our calcium in here, so that is an ionic species. Ionic, so we don't need to draw it. Then we have BF3. We have BF3, so if we have BF3, that is molecular from where we saw it on the periodic table. Then to figure out if it's polar or non-polar, I want you to draw it. So it looks like this, and please hold. I'm going to pause again, guys. Okay, again, we're back. Sorry. Yeah, we have BF3, and boron is okay just having the 3, so there are no lone pairs on it. So it is non-polar. And then we have, next we have CH4. So we go over here and look, CH4, H doesn't count, remember, for those. So CH4 is gonna be a molecular species. Molecular. And then our next step is to draw it out to figure out if it's polar or non-polar. Looks like that. All our formal charges are 0. This is going to be a non-polar species. Okay, then we have our H2O next. I'll just draw it over here. H2O, NF3, LiCl. H2O. So whereas H2O, we have HNO, so that's molecular. What do we do if it's molecular to figure out if it's polar or non-polar? Draw the Lewis diagram. H2O. Is this going to be polar or non-polar? Polar. So you have the lone pair on the central atom. And then if it's polar, we can check for hydrogen bonding. And what's our other requirement besides it being polar for hydrogen bonding? It must have a hydrogen bond to a freak of nature, and that's what we have. So this is hydrogen bonding. Then we have NF3. Where's that on our periodic table? NF3, that's molecular. It's molecular. How do you figure out if it's polar or non-polar? Draw it out. NF. And then nitrogen wants those 5 for its formal charge to be 0, so lone pair. You could throw all the lone pairs on fluorines if you want. And then is this polar or non-polar? Polar. We got the lone pair on the central atom. Is this hydrogen bonding because it's a freak and of a nature? Freak of nature? We got F and N? No, not hydrogen bonding because there's no hydrogen. So this is just polar, not hydrogen bonding. Then we have LiCl. Where's that on our periodic table? LiCl, that's our group 1. Cl, so that's going to be, say it with me, ionic. Dope. So it's an order of increasing boiling points. So our ionic are going to go here because they're stronger than the rest. Then our hydrogen bonding is next strongest. Then our polar. And then our things with London, that's our non-polar. Our non-polar things are the one with London. So we already know where some of these things go. So how do I differentiate between our 2 London, our 2 non-polar? Does anyone remember? We look at our molar mass. So let's do some calculations. What is our mass for boron? It's like 11 plus 3 fluorines. Fluorine's like 19. So if I do that math, 3 times 19 plus 11 is like 68. Then carbon is 12 plus 4 hydrogens, which are 1. That gives us 16. So more massive the stronger. More massive, stronger. So BF3 is going to go there. CH4 is going to go there. Then our polar molecules next. NF. Oh, sorry, not NH. NF3. Then H2O, because hydrogen bonding is stronger than other dipole-dipole interactions. And then we have to compare our 2 ionic species. So that was our CaCl2 and our LiCl. So how do we compare ionic species? Remember charge and then size. And we're comparing CaCl2 and LiCl. So let's do our charges. Ca is +2, Cl is minus, Li is +1, Cl is minus. Larger charge, so stronger. So CaCl2, LiCl. And then it's going to be our final order. Good job, guys. If you have any questions, let me know. And yeah, email me if you have any questions. I'm rooting for you guys. You know how to do this, I promise. Yeah, peace and love. Have a good weekend.